Good morning to everyone. This is Sai Deepak from Computer Science Department. Today's my TechTalk topic is compiler design for distributed quantum computing. Introduction to compiler design for distributed quantum computing. Quantum compiler design plays a crucial role in the optimization and execution of quantum programs in distributed quantum computing environments. Distributed quantum computing involves multiple interconnected quantum processors working together to solve complex problems. The design of compiler for distributed quantum computing aims to efficiently allocate resources, optimize program execution, and minimize communication overhead. Challenges in distributed quantum computing compiler design. In distributed quantum computing, heterogeneity of quantum processors poses a challenge for compiler design. Compiler optimization techniques need to consider the interconnection network and the varying capabilities of quantum processors. Efficient allocation of qubits and gates across multiple processors is essential to minimize communication overhead and maximize resource utilization. Here is an example picture for the distributed quantum computing compiler designs. You can see here these are the qubits and the ABC units. High level language representation for distributed quantum computing. High level language representations such as quantum programming languages provide an abstraction layer for writing quantum programs. Here we can use the quantum computing for a higher level language builds such as quantum programming. This is a programming language we can use for representations. It is an abstraction layer for writing quantum programs. Compiler design for distributed quantum computing involves mapping high-level language context to distributed quantum architectures. Compiler design. Distributed quantum computing involves for compiler design for high-level languages context for the architectures. High-level language representations enable portable and platform-independent quantum programming. Representation of distributed quantum computing is independent quantum program development. These are the key points for the high-level language representation for distributed quantum computing. Moving to next slide, quantum circuit generation and optimization. Here we can learn more about quantum circuit generation and optimization. Compiler design involves the generation of quantum circuits from high-level language representations. Here from compiler design is involved from the generation of quantum circuits from high-level language representations. Techniques such as a gate synthesis, gate decomposition, gate merging are employed to optimize the generated quantums. These are the techniques: decomposition, gate merging, and these are the for optimizing generated quantum circuits. Optimized quantum circuits aim to reduce the number of gates and improve the overall performance of distributed quantum. This is the aim of the quantum circuits to reduce the number of gates. Large number of gates to less number of gates to improve the overall performance of the distributed quantum programs. This is the compiler design involves two generation of quantum circuits for the high level from high level language representations to high level to low level languages. Techniques that such as gate like gate synthesis, decomposition. These are the employed to optimize the generated quantum circuits. The next moving to next slide. Resource allocation and mapping. Here we go to move resource allocation. Resource allocation involves efficiently assigning qubits and get to different quantum processors in distributed quantum computation. It allows resource allocation. It involves for efficiently uh, com- with comfortably assigning qubits. Means appointing a qubit and gets to different different quantum processors in distributed quantum computing systems. Mapping. Here we are going to know about mapping algorithms. Mapping algorithms consider the connectivity of quantum processors and characteristics of quantum problem to determine an optimal allocation strategy. Mapping is nothing but it's algorithms consider the connectivity quantum and characters of quantum and determine the optimal allocation strategy. Effective resource allocation and mapping minimize the need for long-distance qubit connection, reduce the impact noise and errors. Resource allocation and mapping is used to minimize the need for the distance of qubit communication, reduce the impact of noise and errors which are impacting on resources. These are the we can see here the points for allocation and mapping. Next, moving to next slide. See here the example for these are layers. Q naught is these are the qubits Q naught, Q1, Q2, Q3, Q4. One qubit gate, two qubit gate. These are the examples we can learn this in slide. Communication minimization techniques. Communication overhead is a significant challenge in distributed quantum computing. Communication is an overhead for describing challenge in distributed quantum computing. Computer design incorporates techniques to minimize communication between quantum systems during or visited. Comparison is a incorporates technique. Incorporates techniques to minimize communication between quantum processors during the program execution while running the program. Techniques such as gate merging, circuit reordering, and qubit swapping. Swapping means moving from one to another. This is swapping aim to reduce the need for long-distance communication. Communication minimization techniques is aimed to reduce the need for long-distance communication, and this is comparison user techniques to minimize communication between quantum processors and during program execution. Communication already is significant challenge. Next slide. Error correction and fault tolerance. Compiler designed for distributed quantum computing needs to consider error correction techniques to mitigate the impact of noise and errors. Fault tolerance mechanisms such as quantum error correction codes are integrated into the compiler to ensure reliable program execution. Compil- Compiler optimization techniques aim to minimize the overhead of error correction while maintaining program accuracy. Here this is here the issue. Compiler optimization use it to aim to minimize overhead of error correction while maintaining program accuracy. Compiler is for distributed quantum computing needs to consider error correction. It is used to error correction is not used to maintain the without errors correction without error and it corrects errors and fault tolerance. Fault tolerance mechanisms such as quantum error correction codes are integrated for the compiler issues. Performance evaluation and benchmarking. Compiler design for distributed quantum computing involves performance evaluation and benchmarking of the implemented optimizations. Here you can see compiler design for distributed quantum computing involves performance evaluation and benchmarking the implemented optimization. Quantitative metrics such as execution time, resource utilization, and communication overhead are used to evaluate the effectiveness of the compiler design. Benchmarking against standard quantum problems helps assess the performance of the compiler in the different distributed quantum computing scenarios. So the next slide, integration with quantum networking. Compiler design for distributed quantum computing needs to integrate with quantum networking protocols and technologies. You see, integration with quantum technologies integrate with quantum networking protocols and technologies. Integration enables efficient communication between distributed quantum clusters and facilities execution of distributed quantum algorithms. Compiler designers collaborate with quantum networking researchers to leverage advancements in the field. The image keeps compelling algorithms networking, qubit assignment, non-local gate and handling. This is execution management, simulation, therefore physical technology, virtual creativity. Next slide. Conclusion. Compiler design is crucial for efficient and optimized execution of quantum problems in distributed quantum computing environments. Challenges such as heterogeneity, resource allocation, communication, minimization, and error correction need to be addressed.